Okay. Uh, Good evening, everyone, to the last and final session of EAC's Computational Physics cases. Today, uh, till now, we have looked at uh, basic programming in Python, linear ordinary differential equations, non-linear ordinary differential equations, different methods of discretization, and today we will be taking a short look at partial differential equations and how we can model complicated systems which occur in nature, in more than one dimension. So I'm going to share my screen now. Is my screen visible? Can someone answer, please?
Yes.
Yeah,
Okay. Okay. So before diving into the session, I want to give you a short background of why we are exactly what partial differential equations and what we are learning. So we have seen equations of this form. Okay, and not equations, functions. We have seen functions of this form, and these are very common. Okay, and whether we talk about our position as a function of time, we talk about velocity as a function of time. We talk about acceleration as a function of time, maybe force as a function of time, or maybe in some cases, force as a function of uh, distance. So these are all single variable functions, and these are they form ordinary differential equations, and they're fairly easy to solve compared to partial differential equations. What are partial differential equations? They are functions of this kind, uh, which may involve or fold all the coordinates and time. Okay, and they are fairly complicated to solve, uh, by hand, because they involve derivatives like dou u over dou x, dou u over dou y, dou square u over dou t squared, something like this. Okay, so they might involve these sort of derivatives, and these sort of derivatives are pretty complicated to handle, because when you integrate this, you will not just get when you integrate this kind of a function, suppose, you will not just get u plus some constant c, you will get u as a function of u plus an entire full function of the rest of the variables. Okay, so boundary conditions are a little hard in this sort of a scenario. So what do? We have various methods of finding an actual solution, but we prefer numerical methods in when it comes to partial differential equations. Now, why exactly? For that I'm going to give you an example. Now, there are three main categories of second order partial differential equations, and I'm going to write them all down. This is Laplace's equation. Um, then there is, one second. Yeah. Okay. This is called the heat equation, and then there is the wave equation, which I'm sure you guys must be familiar with by now. Okay, and I am considering for now for these to be a function of just x and t, or x and y. That is just two variables for now. Okay, This is now these have certain names to them. This is called an elliptic equation. This is called a parabolic equation. This is called a hyperbolic equation. Now, why it is called that? Because they sort of resemble your algebraic equations for your ellipse, parabola, and hyperbola, and they have some really certain nice properties to them. But we will not delve into that. And we will also only deal with the heat equation because it gives very nice bounded solutions for most of it, for most of the boundary conditions, and that is to be known. Now, does anybody know what u here actually is in the heat equation? What can u be when we are talking about heat? You know, what can u actually be? This function u. What does u represent? U of x comma t. What does this represent? Anybody? Okay, since there are no answers, U represents temperature. And we know the temperature of any system tends to stabilize. Okay, so this way, and we can come up with some nice boundary conditions and all for boundary as well as initial conditions for the equation. Okay, now let's talk about, so how do we go about solving this? A very common way to solve this is to consider u of x comma t to be a function of x and a function of time. A product of a function of x and a function of time. So we can put this in the equation, and what will we get? We will get x of x t dash of t equals to alpha times x double dash of x and t of t. And we can rearrange this. We can say 1 by alpha t dash of t over t of t, and you will see why I'm rearranging this in a second. Okay, so what does this say? This is just a function in t and this is just a function in x. Okay, so when can two functions which are of absolutely different variables be equal? Can someone unmute and answer if they know the answer? Or take a guess at it, even that is fine. Anybody? Okay, seems like not. It can this has to be an equals to a constant. Okay, and we take that constant to be negative k squared. Why do we take a negative constant? There are variety of reasons. You can take a positive constant. You can see that the solution that you get will not be bounded. It will be it will keep on increasing forever, which is not exactly what we want. So we will take a negative constant here. I want you to test out taking a positive constant, taking a zero constant, what kind of solutions you will get for that. So from this we will get two ordinary differential equations, minus alpha k squared t and x double dash of x equals to minus k squared of x, and we know how to solve both of these equations. Okay, that simplifies our work by a lot. And when we solve these two equations, we get t of t to be a times e raised to a minus alpha k squared t, and we get capital X of x to be c1 sine kx plus c2 cos kx. Okay, and we know u of x comma t is a function of these two. And I will just absorb a into these two constants. So I'm just going to Yeah, I'm going to absorb a into these two constants. So I'm just going to write e raised to power minus alpha. I'm going to write this a little below. Yeah, okay, I now can write e raised to power minus alpha k squared t a sine kx plus b cos kx. Now this is what a general form of a solution is. Now after this we have boundary conditions, and we will be using these boundary conditions, and these are called Dirichlet conditions, over named after the mathematician Dirichlet. 0 comma t is 0 and u of L comma t is also equals to 0. This basically, what does this problem mean? This problem means that I have a rod of length L. Okay, this is of length L. Okay, and this is x equals to 0, this is x equals to L. Okay, and basically at this point at my temperature is 0, my this point is this is initial condition, so temperature is not 0 yet at. Okay, what happens is at t equals to 0 I have some distribution, okay, of some temperature. Maybe it's a temperature is distributed like this as a sinusoid, or maybe it's distributed like this, something like this. There's a temperature distribution over this. Okay, and I want to find, and at t equals 0 what happens is these 2 points, they are cooled down to 0. Okay, they become absolutely 0, and when that happens, this heat will obviously flow, and this entire rod will tend to go towards 0. It will get cooled down eventually, and that is what we want to find, how what is exactly will be the variation of that cooling. Okay, now all of this is very complicated. Okay, even if we find the solution, it will be a series solution of suppose this form a n sine of k n of x n equals to 0 to infinity uh, into e raised to power minus alpha k n squared t. This becomes u of x comma t, and you can find your kn is something like n pi over L, and you find your an as an integral of um, wait, okay, some integral of this form f of x sine of kn of x dx. Okay, so you can see this is a lot of work to get an you know to get an to get a closed form expression. Okay, so this is a lot of work, and it doesn't give us too much good information, because first of all this is a series solution. Okay, a series solution is good when it comes to mathematical calculations, but numerical calculations not so much, because we have to make approximations again. So rather than doing that, we can just apply our numerical methods. That seems much more simpler. So how do we apply a numerical method? Let's do this. This is our original equation. Do u over do t. Okay, now this portion I know how I can discretize my double derivative. It will be something like u of n plus 1 minus 2 u of n plus u of n minus 1 over uh, delta x squared. Okay, and this side becomes, and this is all. I'm going to represent my time as a subscript and my position as a sorry, my time as a superscript and my position as subscript. Please do not confuse these to be powers. These are not powers. and I can, discretize my time to be I plus 1 minus u of I at same position delta t squared. Okay, so now I have somewhat of a, you know, now I have somewhat of a, you can say, method. This is not t squared, this is just t. Yeah. Now I have somewhat of a method of, you know, finding what my temperatures are. Okay. Now look, let's see what this equation actually means. What this equation means is at u of 0 n, okay, of u of 0 n. Now I want to look at my boundary conditions. At it is talking at t equals to 0. So my I here should be 0. Of u of 0 n, I have my temperature distribution to be f of xn. Okay, which means at x position 1, x position 2, x position 3, which is what these indices correspond to. Okay, this is my first boundary condition. This is my boundary condition. Now, sorry, this is my initial condition. Now looking at the boundary condition, u of 0 I, this will be 0. Okay, at any time t, the first index would be 0 and u of ni is also 0. What is n? N here is the number of intervals we divide our length in. So if we have a rod, say this thing, okay, we will divide it up into n portions. Okay, this is rod of length L. We will divide it up into n portions. So the 0th index will correspond to x equals to 0, and the nth index, nth index will correspond to x is equals to L. So now I formulated my entire problem as a discrete system. Okay, there is another way to look at this, which is a much more graphical solution, so it's easy to imagine. Let's consider our u's to be each u to be a point on the grid. Okay, here this increases my I index, and this increases my n index. Okay, so here this is x equals to 0, this is x equals this is xi, this is x0, this is x1, this is x2, this is x3 till this is xn. Okay, something like this. So I know the value of each of these. Okay, since I know my value at of temperature at x0, 1, 2, 3. Okay, so I know my value. I know these values. u0, u1, u2 till un. Okay, I know these values. Now I need to find these values. How do I find these values? I know that this first value and this last value are 0. Okay, since I know these are 0, now I need to find this value. For this value, what do I need? This is an average of this 3. So I will need value from here, I will need value from here, and I will need the value from here. And this way I can find this point. Similarly, for this, I can find value from these 3 points. And like this, I can find all of these. Okay, now I have this whole row. Similarly, for next, this is 0, this is 0. I will find values for this thing. Similar, this will keep continuing till I want. Okay, till my time, till however much time I want. This will keep going. So that is precisely what we are doing here. We are using the average of these values to find, not average exactly, you can say a weighted average of these values to find, each point, and we know the first and last point is 0 given our boundary conditions. And whatever values we get at the absolute end, okay, that becomes our final temperature distribution. Okay, and these, all of these are intermediate, temperature distributions of the rod. Okay, now let's take a look at the code. Let's take a simple function. Let's take math dot sin x. Now I have given some value to constants. I have taken alpha to be 0.1. Now what alpha is, it determines your rate of heat transfer. It's not really important here, but if you're interested in the study of the heat equation, it comes up pretty often. L is the length of your rod. Okay, how I've taken it to be 10 units. N is the number of divisions. That's how many divisions do you break your rod in, and each division is dx. Okay, so L by n. Similarly, each time step is 0.1, and I want 100 iterations. Let it go. Let me find it for 100 time steps. Here again, I have declared an array of time steps. I have declared time step vector. This is just a constant, which is this thing. I've just made this as k, for our convenience. Then this is the position step vector, like how we have a time step vector. Now we also have a position step vector because that is also a function. That is also a variable. And this is the array in which we store all our u's in. This is basically a n plus 1 and I plus 1 array. Now what this loop does is it assigns a value of f of x 0 to u0, f of x1 to u1 for all t. So that is basically what it means here. Now for the actual algorithm. Now algorithm, you don't have to think much. You just copy down whatever you take. So you have your j and your I indices, and you just write everything down in terms of you're accessing your elements in the array. Okay, and then you apply these boundary condition that is, and of making the first and the last point in that whole grid 0. Yeah, you make these 2 points always 0. That is what you're doing basically, and you just run this. Now you will see when I plot this, I will plot 10 graphs here to show you snapshots. This is my system at t is equals to 0. Okay. Then this is my system at t equals to some okay 3, t equals to 3, t equals to 5, t equals to 7. Yeah. So, or rather not t, I should say n is equals to 5, 7, because these are time steps rather than the time. You multiply that with 0.1 and you will get the time. So t equals to this is t equals to 0, this is t equals to 0.3, this is t equals to 0.5, 0.7. So what do you see here? You see that the middle part is gradually flattening out, and all of the disturbances are getting accumulated to the side, which is kind of what we expected to happen. If heat flows from hotter regions to colder regions. So if the middle is hot and the sides are cold, the heat will flow to that region, and you will see that the sides, the disturbances keep accumulating. Okay, and finally all of the heat just flows out of the rod, and this will happen sort of in in all conditions. So there I've taken the distribution of sin x. Here I'll take a linear distribution. You will see the same thing happening here. the temperature in the middle of the rod gradually decreasing, accumulation to the side and passing out. Similarly, if you want, suppose this kind of a boundary, here you will see something different. Here you will see heat getting accumulated on both sides and passing out. Okay, so this is basically the theory of your heat equation, and this is a very basic way of solving, you know, solving for your temperature conditions. Okay, these are all Dirichlet conditions. You can also there's something called Newman conditions, and there's something called, I'm not sure. There's other kind of boundary conditions that you can use, and that basically gives you your numeric, the conditions for this iteration to be applied. Okay, you have this sort of a iterative method, and you just need a certain value to calculate it. Yeah, sorry about that. Okay. Is there any doubts till now? Are there any doubts? Okay. So that is it for today's session. Thanks for joining, guys. Please stick around for a second.